Hi, and welcome back to Codex. Today's speaker is Dave Jekel from the University of Copenhagen. Dr. Jekel is an expert in operator algebras, random matrices, and quantum information. Today, he'll tell us about asymptotic freeness. Take it away, David.
Yeah, thank you for the introduction and invitation. So yeah, this is joint work with Srivatsa Kunawalkam Valley. So since I know this seminar spans of many topics, I wanted to start out just uh, giving a basic introduction to what asymptotic freeness is. So this is an important work, a result of Voiculescu that describes the large n behavior of independent random matrices in many different situations. And so in particular, what we're interested in for is several random matrices. There'll be n by n matrices. And so they'll be indexed by n in the superscript, and then we also have several matrices indexed by the subscript. And what we're interested in is non-commutative moments, which is if you take some word and take some product of these matrices and then try to study the large n limiting behavior of this. And Voiculescu showed this large n behavior was if the matrices are independent, then under some mild hypotheses, you get in the limit this concept of freeness, which is a non-commutative form of independence that comes out of von Neumann algebra theory. And to give the most basic example, right, that you can give without without giving further definitions, you consider the case of Haar unitaries. So these are independent unitaries that are chosen kind of uniformly at random in the n by n unitary group. And then you compute some expression which is a product of some of these unitaries and their inverses. The large n limiting behavior of this, the normalized trace of this will either go to 0 or will go to 1, almost surely. It will be 0 only, or it will be 1 only in the case where it's forced to be 1 because of everything canceling, right? Meaning that the expression that we've put in here is actually the identity as a word in the free group. And then otherwise, the limit will be 0. And so what this is showing is that somehow the large n behavior of the random unitaries is described by the free group on the correct number of generators. So in case some of the definitions of these objects were not clear, to be more explicit, what do I mean by Haar unitary? Well, anytime you have compact group, or more generally often for locally compact groups, then you have some shift invariant measure. Okay, so for compact group, you have a unique shift invariant probability measure, which is the Haar measure. So there's a unique kind of uniform measure on the unitary group. And then the Haar random unitary is a random variable, right? So in the sense of probability theory, so I'm using probabilistic notation. And so the measure of the set with respect to the Haar measure just means the probability is equal to the probability that this random variable lands in that set. Now, to give further motivation, let me tell you what happens to just a single unitary, right? So the theorem I stated in general was for several independent unitaries, but if you were to just look at the case of a single unitary, where you just like take the product of the unitary with itself several times, what happens? Well, you could express this, these traces that we're studying then can be written in terms of the eigenvalues. So if you look at the eigenvalues of the matrix, which are still random, then you look at something like the average of the kth power of the eigenvalues, and then this will be converging as n goes to infinity to 0 or 1, and it'll only be 0 if k is, or it'll only be 1 if k is 0. And what happens, and you can view the large n limiting thing as the integral of a function over the circle. And so the same holds if you take a continuous function, then the trace of this function applied to the unitary matrix, or the limit of the average of this function on the eigenvalues, is converging to the integral of this function over the circle in the uniform measure. Right, and this follows from the theorem here, because in the case where you just apply the same matrix several times. And with Voiculescu's asymptotic freeness theorem, the main point of it is that it describes what happens when you mix several independent matrices together in these expressions. Yes. So what is this asymptotic freeness theorem useful for? There are a couple of applications. So one thing that's happened in the last 5 or 10 years, they use this random matrix theory to study the initialization of neural networks, because neural networks are often like given a random initialization, and this is actually important for making them work properly to learn from the data that they're given. So another application, which was given by Hastings a while ago, is that you can use these independent unitaries to generate a quantum channel, which is a quantum expander, which is which is the sort of thing you would want to use for building some kind of error correcting code. Okay, so then the third example is something which I worked on recently with Jaspreet Singh Sandhu, who's at another campus of Colorado State, as well as Jonathan Shih. And that is that we're studying spin glass theory, which is some kind of statistical mechanics thing, and in particular, the so-called Sherrington-Kirkpatrick model. And the main point here is that the input to this model that allows you to build the Hamiltonian is a Gaussian random matrix. So we use this random matrix theory and free probability tools in order to study that model into, as an ingredient for a bunch of other constructions for that. Another application in the realm of non-commutative algebra is that you can look at the field or the skew field of non-commutative rational functions with this free skew field, which actually is a bit involved to even define what it is. But then if you want to take a matrix over this free skew field, and then you want to determine what the rank of it is just abstractly, algebraically, you can actually compute that by plugging in certain freely independent things into the entries of the matrix for the variables, and then just doing explicit computation of the rank of the spectrum and the rank of that, and then that will agree with this abstract rank. And the last thing is also another thing that I've been heavily involved in, which is analytical properties of von Neumann algebras, because basically they're the large and limiting objects that arise in this theory at like n equals infinity are operators in some von Neumann algebra. And you can actually use the existence of the finite dimensional approximations and the probabilistic properties of the Haar unitaries and Gaussian random matrices and other things like this in order to analyze the von Neumann algebras themselves, because the von Neumann algebras are actually quite difficult to understand in a lot of ways, and somehow using the finite dimensional approximations gives you another set of tools which it proves things that are maybe not obvious from a different perspective. And finally, I should mention, since this is since in the seminar you guys have studied many things relating to Wasserstein distances before, that one of the main things that I've been working on in the last few years has been looking at Wasserstein geometry in this free setting and how to make it actually correspond to the large N behavior of classical Wasserstein geometry for the matrix models. Now, I'm not really going to talk about that today, just because it seems that would require giving a lot more background, and I wanted to present something that's more self-contained. Okay, sorry about this. Okay. Yeah, so here's the main result that I want to present. And this is motivated by something that was done in the von Neumann algebraic setting for free products by Houdet and Yuan. And the theorem says the following. Okay, so we take these independent n by n Haar random unitaries as described in previous slides. And now we take some other random matrices, B1n, B2n, etc. Okay, and these things are basically arbitrary. There's no requirements on independence or anything else. But the only thing that we require is the following, that let's say that the operator norm of them is bounded by 1, and that they asymptotically commute with the matrices uj. So and for this notation, the 2 norm here is like a normalized Hilbert-Schmidt norm, right? So I take the trace of A star A, but this lowercase trace is normalized, right? So it's 1 over n times the sum of the diagonal entries of the equivalent. Okay, so they asymptotically commute in this normalized Hilbert-Schmidt norm. And then the conclusion is that these matrices B1 and B2 n are asymptotically freely independent. Okay, so without any assumptions of independence on the B's explicitly, only the assumption that they commute, right, that they something about their relationship with the UJs, then you actually have the free independence for these BJ matrices. So in other words, we're saying, okay, if you take these Haar unitaries uj, and then if you take these bj's that asymptotically commute with them for each j, then the bj's must be approximately free. Or it's saying that somehow the free independence of the Haar unitaries somehow spreads or like infects these other matrices that merely are assumed to commute with each of the UJs. And there's another way that as you can think about this, which is motivated by the viewpoint of logic in the setting of metric spaces. But that what I'm really saying is I'm making a statement about the UJs that involves quantifiers, that involves quantifying over arbitrary BJs. So what it's saying is that the UJs have this property that for all BJs such that they commute with UJ up to a certain error size, then the BJs have to be freely independent from each other up to a certain error tolerance. So not only is that true, but you can also extend this further. Instead of just having picking one thing that commutes with the UJs, you can also make a chain of things that commute with each other. So I could choose a bunch of matrices, V, J, K, N, with this property that say the VJ1 commutes with UJ, and then this should say K plus 1. VJ K plus 1 commutes with VJK. Right? So I take one thing that commutes with UJ, then I take another thing that commutes with that, and I take another thing that commutes with that. And also I assume that the things in this chain are, say, having an asymptotically uniform spectral distribution on the unit circle, right? So basically, I can't let the things in the chain become trivial, right? Because then, of course, they could just be the identity, and then that condition would mean nothing because everything commutes with it, right? So as long as the things in the chain are having this uniform distribution, then you can actually conclude free independence for those things as well. So you can do the commutation not just after one step, you can do several steps in a row, and then at the end you still get things that are freely. In fact, everything in the first chain will be freely independent of everything in the second chain together as well. So in the proof of this theorem, at least the first case, is not that hard to explain, and I will try to do this in the bulk of the talk. And before I do that, I want to give a bunch more notation and setup for this non-commutative probability set. So what do we mean by non-commutative probability space? So this is formulated in algebraic terms, right? So in the classical case, you would think that the elements of the algebra would be random variables. The algebra itself might be the L-infinity algebra of the underlying measure space in your probability set. So what you're going to have some star algebra. Okay, so you have addition and multiplication, and you have a star operation, which is basically like taking adjoint of an operator or a matrix. And then you have this map, which is called denoted here by tau. And the tau plays the role of expectation. So it takes in a random variable as input, and it outputs a complex number. And the properties that you would want are the following. So the trace of 1 is 1. And this is also a type of trace. Yeah? So the trace of AB is the trace of BA, just like you would have for the regular trace on matrix algebra. And it has this positivity property, right? The trace of A star A is greater than or equal to 0. Right, which should be true because the A star A is always a positive operator, right? So its trace should be non-negative. And finally, if the trace of A star A equals 0, then it forces A to be 0. So if you take A to be the n by n matrices, all these properties are satisfied where this tau is the normalized trace. And then you also would have classical probability spaces, right? So you could take A to be L infinity of the unit interval 0, 1 with Lebesgue measure, and then take tau to be the integral, which would be, you could view this as a sample space in a probability theory, and then this tau would be the expectation. And so basically we have a notion of a space of random variables. They behave very similarly to random variables with some expectation, but they just don't commute in multiplication. And this is exactly what we need to describe random matrices and to be able to construct a limiting object where you could say, okay, not only does the limit as n goes to infinity of this expression exist, but it actually equals to the same expression in some kind of infinite dimensional version of matrix algebra. So another important thing that you can do with this is that you can build a kind of analog of L2 space, right? So if in classical probability, if you have a probability space, then you always have an associated L2 space, right, of the square integrable random variables, or one where the expectation of the absolute value of x squared is finite. And in the abstract setting here, you actually can also construct such a thing. And how do you do this? Well, you start out by taking elements in A and defining an inner product. By the inner product of AB is the trace of A star B. And then after taking this inner product, you can complete this to a Hilbert space. And because on the last slide, I assumed that if the trace of A star A equals 0, then A must be 0, right? Then this means that there's no kernel in this. So this makes sense. And then the algebra A, the original algebra, will act on L2 of A by left multiplication or by right multiplication, right? So there's an action here. And thus, I guess maybe you actually need some mild assumption to guarantee that these will be bounded operators, okay? But this will be true in the situations I care about, right? And so then you can embed the A inside bounded operators on this L2 space by the left multiplication. And this is just like in classical probability space, you can embed L infinity inside the bounded operators on L2 because the L infinity acts on L2 by multiplication. So this is exactly just a non-commutative. So then if you want to do a kind of analysis in this case, where if you really want something analogous to measure space, then you study the setting of von Neumann algebras. So what is von Neumann algebra? It's just assume all the axioms I've said so far about this trace, but then we also assume that A is closed inside B of L2 with respect to the weak operator topology. And the weak operator topology, it's not important for this talk what the definition is, but it is that something converges in the weak operator topology if the inner product of it with any pair of vectors converges. And this weak operator topology really, if you compare to the commutative case, this corresponds to taking the weak star topology on L infinity as the dual of L1. And so then if you want something that behaves like really an L infinity space, then you want this von Neumann algebra. And besides these examples of matrices and classical probability spaces, another very central example is group von Neumann algebras. So if I take a discrete group, and then if I take the square summable functions, the L2 of the group, then I have certain unitary operators on the group, which are given by left shift by each group element. Okay, so you have these shift operators acting on L2 of the group, or the infinite dimensional left regular representation of the group. And then then what we denote by L of G is the group von Neumann algebra with the von Neumann algebra that's generated by these unitaries. And so this can be thought of as a kind of completion of the group algebra with respect to this weak operator topology, because this thing contains canonically this copy of the group algebra. And as an example of this, right, if you were to take the group von Neumann algebra associated to the integers, then this will actually be just the L infinity space of the circle. And this is just by Fourier transform, right? Because you could say that you could see the L2 space of the group, right, by the Fourier transform is transformed into the L2 space of the circle. And then the shift by a group element in the group picture turns into multiplication by a complex exponential in the circle picture. And so then when you study this, in a sense, this is like a non-commutative Fourier analysis or something when you study the von Neumann algebra associated to the group. But in this case, if the group's not commutative, you can't transform it into a classical L infinity space. But this kind of setup motivates the notion of quantum groups, for instance. Okay, so if you look at this case of groups, and if you consider what happens when you take free products of groups, and like what would happen to the von Neumann algebras, then you would naturally get to this condition of free independence. And this was formulated by Avytsur as well as by Voiculescu around the same time. And so the free independence has the following definition. Okay, so you have this non-commutative probability space. You have subalgebras indexed by some index at I. And then you say that they're freely independent if the following is true, that if you take an alternating sequence of indices, right, where the consecutive indices are not the same, and then if you take elements from algebras corresponding to this sequence of indices, and then you subtract off the trace of each element times the identity, then now the product of these things will have trace 0. And so you can think of this in the group setting because in the group von Neumann algebra, the things that have trace 0 are exactly the span of the non-identity elements. So basically, like, this is analogous to saying that you take a product of non-identity elements from the individual groups, where the consecutive indices are not the same, and then the product will be a non-identity element in the larger, right? Which is basically the definition of free productive groups. So this is like you just replace non-identity element by elements of trace 0, and then you come to this definition. And so then, for example, if you were to take your algebra to be the von Neumann algebra of a free group on infinitely many generators, and the trace, which maybe I forgot to mention in the last slide, but the trace for the group case is the trace is 0 if your group element is not the identity, and it's 1 if it is 0. Yep. And so then the algebras AI generated by the different generators in the free group will become freely. So once you define free independence, then you can also define like an asymptotic version of it, which is what applies in the random matrix setting. Because in the random matrix setting, they're not going to be exactly freely independent, because that could only happen in an infinite dimensional von Neumann algebra. Okay, but they will be asymptotical. And so asymptotic free independence would mean the following. Okay, so you take some, say, x's, which are matrices. Okay, and for simplicity, let's assume that the operator norm of them is bounded as n goes to infinity. And then free independence would mean that if you take some polynomial in the x's, and then you subtract off the trace, and then if you take the product of these things, right, with indices that are alternating, then the trace of this will converge to 0. So asymptotically, it will satisfy this freely independence. And of course, in probability theory, you can make such statement in expectation, or you can make it in probability, or you can make it almost sure. And I think in most cases, mine would be almost sure. So hence, right, Voiculescu's result, in the case of Haar unitaries, would say, for example, that these Haar unitaries are almost surely asymptotically freely independent. And similarly, you can have various random matrices, like if you've heard of Gaussian unitary ensemble or Gaussian orthogonal ensemble, right? And if you choose independent copies of random matrices in those distributions, then these are almost surely asymptotically freely. So now let me come back to trying to prove the main result, right? So remember, the main result is about, you start with some independent Haar random unitaries, it's a U sub j, and then you have these other matrices B sub j, and each B sub j commutes with the corresponding U sub j asymptotically. And our goal is to show that the B sub j's are freely independent. Right, and so how are we going to do this? And there's basically two ingredients, and this is exactly how Voiculescu's asymptotic freeness theorem is also proved. Okay, so I mean, first you have to know that the expectation of the thing that the thing that you want to go to zero, you first try to show that the expectation of it goes to zero, and then you have to upgrade from the expectation to proving almost sure convergence. And then that upgrading occurs using concentration of measure. So that's a concentration of measure is something that often happens in high dimensional models. And what it means is that basically if you take, say, a Lipschitz function of that's real valued of the random variable, then with high probability, the value of this function will be close to the expected value. So it basically, so the value of the function basically concentrates, right? And so maybe the most classic example of this that you might be familiar with is that if you choose a random point on the sphere in high dimensions, right, then it's very, very likely to be at the equator, right? Or if you were to take the coordinate of it in a single direction, then that is likely to be very, very close to zero. So that's such a concentration results for the sphere. So then what we're going to try to do in our theorem with these matrices Bj, okay, so we don't really know exactly what the Bj's are. There could be many, many options for what the Bj's are. But basically what we're going to do is show that we can handle all possible options for what the Bj's could be at once, uniformly. Okay, so we'll look at the set of matrices that approximately commute with U1, and the set of matrices that approximately commute with U2, and so forth. And then we're going to just look at that entire set of matrices that commute with U1, and then choose an epsilon dense subset, right? So you choose some set where everything is within epsilon of one of these finitely many elements. And it will turn out that the total amount of elements that you need to cover this space of matrices that approximately commute with U1 is relatively small. So there are not that many elements that you need to approximately cover this space, right? And the same for each of the unitaries, right? You have this space of things that commute with it, and it's covered by a relatively small number of elements up to an error of epsilon. And so then we'll just use the concentration of measure, and we'll just do a union bound over all these elements, and we'll still be able to win and say that almost surely the limit of the thing is zero, because you have relatively few elements and you have a very strong bound on the probability of error from the concentration. So that's the basic outline of the argument. Now, how does this go technically? If you want to argue, why does the space of things that commute with U1, why is that able to be covered by relatively few balls? It helps to change coordinates a little bit by diagonalizing the matrix. Right, so we could take, so originally we were studying this Haar unitary Uj. And what we could instead study is take a deterministic matrix AN with evenly spaced eigenvalues around the circle, right? Eigenvalues that are just roots of unity. And so then we could take that diagonal matrix and then we could take that and conjugate it by a Haar random unitary so that you're kind of uniformly choosing the directions of the eigenvectors. And what I claim is that this VJ, VJ star, and the UJ are close to being the same in distribution. Right? So it's actually so there you can choose a coupling. You can put a copy of UJ and a copy of VJ in the same probability space, such that the operator norm of UJ minus the conjugation of AN by VJs goes to 0. So maybe I don't know if you're not familiar with this, that may seem like a weird statement, or why is this exactly true? But it actually is not that hard to prove, and in order for this to work, it basically just it's enough that the spectral distribution of the UJs is converging to the uniform distribution on the circle. And as long as that is true, then that's basically all you need to guarantee that it's conjugate to something that's close to this A. And then the fact that this VJ here is chosen uniformly, it just comes out of the fact that the Haar measure on the unitary group is conjugation invariant. So this has to be the right thing to do. So then in the rest of the argument, right, I'm going to just use these coordinates. I'm going to pretend that the UJ is actually just the conjugation of the fixed matrix here by this VJ. Why does this help? Okay, well, that's because once we have this AN explicitly, then it's easier to just write down by hand, like, what does it mean to approximately commute with it? Okay, so first I'm going to take this BJ, right? Remember, the BJ is assumed to commute with the UJ asymptotically. And then I also write a conjugation of that so that to change coordinates, right? Use the same VJ to conjugate this back, and then you get something that asymptotically commutes with this AN. Okay, so now what does it mean to commute with the AN? So you can compute this a bit by hand, right? So you take this diagonal matrix A times CJ minus CJ times A, right? And since the A is diagonal, what it's going to do, if you multiply it on the left, then it's going to multiply each column by the corresponding root of unity. And if you multiply it by it on the right, it will multiply each row. And so then if you subtract these two things, what you'll get is in 2 norm, you're going to get the squares of the absolute value of the entries, and then it will be multiplied by the difference in the corresponding eigenvalues which came from the left multiplication or the right multiplication by the diagonal matrix. And and since the eigenvalues are evenly spaced, then this is sort of up to bounding above and below by constants, basically like the difference between the indices, modulo n, and divided by n. So basically what that means is that if it almost commutes, that's happening when the non-zero, or most of the mass of the matrix C is concentrated in this band around the diagonal, right? The periodic band, certainly, but it's basically a band. There's a band around the diagonal where you could have something, but then outside of that band, everything would have to be pretty small in the total mass. And so then you could actually define this set here. You could define matrices in an epsilon band around the diagonal. So matrices where the entries are 0 if the distance of the indices mod n is bigger than n times epsilon. And so then the claim is that if you have some things that are, say, bounded in operator norm, and then if they asymptotically commute with the AN, then the distance of the Cn from this diagonal band of width epsilon will go to 0 for each epsilon. Yep, so it's basically asymptotically, things that commute with it are basically like band matrix. And also, if you want to be more precise about this, right, you can find something which is close to Cn, right, and is in this diagonal band, is in this diagonal set, without increasing the operator norm too much. Okay, so now I'm going to tell you, more precisely about this covering argument. Okay. So, or actually, no, not the covering argument. Yeah. This is just now what happens for a fixed element. Okay, so from Voiculescu's asymptotic freeness theorem, you have the following fact. Okay, if I were to just fix one choice of C, right, if it was something deterministic, and then if I were to conjugate it by these independent Haar unitaries Vj, then these will be asymptotically free independent. Right, and so this is this precise statement, right? So if you take this, you subtract off the trace, and then if you conjugate by this Vj's and then take the product, then the trace of this will go to 0. And then here, if I take it in expectation, right, then yeah, I mean, I can plug in any C's that I want in the unit ball of matrices, and this is a uniform bound on the expectation. And then the whole rest of the argument is basically to say, that you don't have to take expectation, but that you can just prove the statement almost true. Yeah, so the expectation of the thing that we want to be 0 asymptotically, this has already been taken care of by Voiculescu's results. Okay, and then we can move on to the concentration of measure arguments. Right? And this also is uniform. It doesn't matter which things you put in as long as they're in a unit ball with respect to operator norm. So then we come to the concentration estimates, and below this you can see several references where for people that develop this result. Okay, so if you have independent Haar random unitaries, and then if you have a Lipschitz function, and we're assuming we're measuring the Lipschitz norm here by using this normalized Hilbert-Schmidt norm for the domain, right? That affects the normalization of what I write then. And then the probability that f of x differs from the expectation by delta is bounded by exponential of minus n squared delta squared over constant times the Lipschitz norm squared. Right? So this is, as n goes to infinity, right, this probability is extremely, extremely small. Like exponential of minus n squared times some positive form. So now we come to this concentration argument. Okay, how does this go? I'm going to start out with some sets. So I'm writing this in a bit more generality because actually there's more general versions of the theorem. But we take this set Sjn. Okay, and for purposes of this main theorem that I stated at the beginning, this Sjn could be this space of epsilon band matrices, right? This band of width epsilon. So you should think this is what the Sj is. And so then if you have that the covering number of this space, right, the number of balls of radius epsilon that you need to cover this set, and if this 1 over n squared log of the covering number is asymptotically less than delta, okay, and basically that means that you can cover it by e to the minus n squared delta many balls of radius epsilon. Right? So if you have this assumption on the covering numbers, then you could say that this quantity that we want to compute will be asymptotically less than something depending on the epsilon and delta. And this is now uniformly for all the choices where x1 is in S1n and xk is in sk. And so forth. And this is not an expectation anymore. This is just almost surely, right? So almost surely this supremum over the x's in this set of this expression that I want to be 0 will be bounded by this. Now, maybe for the sake of time, I won't go into detail here, but it's basically just what I said, that you apply, you choose this epsilon dense subset, and then you apply the concentration inequality for the value of this functional on each of the things in the subset. And then you say that if I take an arbitrary element and it's within a distance of epsilon of one of these finite lists that I've already controlled, and so then you just get another small error depending on epsilon from. So yeah, I guess I'll let you read this later in the slides if you want to go into more detail. Okay, but basically, you have our assumptions guarantee that you have exponential of like n squared delta, many elements in my epsilon dense subset. The probability of error being a certain size is e to the minus n squared k times delta. And so then if the constants are chosen right, then this small probability will overwhelm the large number of elements in the subset, and so then we'll get something which is still exponentially small. And then you use the Borel-Cantelli lemma because the probabilities are summable, right? And then almost surely, then like the events will happen if we're sufficiently large. Okay. So then here, this is the estimate for what the covering number is explicitly for this epsilon band. Okay, and this is just kind of a direct computation because the epsilon band is like something, a ball in a space of dimension epsilon times n squared, right? And so then you just plug in standard computations for covering number of balls, and this is what you get. And so then this will be the delta in the previous lemma. It will be epsilon like log 1 over epsilon. So what's this here? Maybe I will skip this because I don't want to go into technical details here, right? But basically, from the arguments that I've sketched so far, then you can argue that the BJs will be in this space of things that almost commute with it. And then also if you were to take a polynomial or some function of the BJ, then that would also be in a certain space with covering numbers that are relatively small. And so this preceding reason. Okay, so let me spend the last few minutes mentioning some generalizations of this. So I proved all these results, right? I just used the space of matrices that approximately commute with the UJs to do this covering argument. But there's many other things which have small covering numbers which you could use instead. And so it actually, the argument here gives you there's a lot of other things that this applies to as well. And there's actually a kind of a systematic study of covering numbers of the spaces of matrix approximations for some von Neumann algebra. And that gives you this notion of one-bounded entropy. And I guess similar things were in papers of Hadwin and Ge, and so forth. But then this really was crystallized in the work of Zhang and of Hayes. And it allows you to study various structural and analytic properties of the von Neumann algebra. What is this one-bounded entropy? Basically, you define it to be the covering number of spaces of matrix approximations for the generators of your von Neumann algebra. And you also have it a technical variant that you have one smaller von Neumann algebra inside a larger one. And so you look at matrix approximations of the smaller von Neumann algebra, which can be extended to some matrix approximations of the larger algebra. But then you just look at the covering numbers of them, just covering numbers of just the coordinates that represent the smaller element, right? So you don't care which extension to the larger algebra there is, it's just you care that it exists. And then you take the appropriate limits and you define this quantity H. And this H has a sort of analogy with dynamical entropies, because there's various forms of dynamical entropy. Say if you have in integers acting on a space, or if you have a amenable group, or if you have Sofa group, you can define various types of entropy. And the entropy is often defined by looking at some kind of finite finitary objects, right? So either you could look at finite orbits, right, in maybe the most classic case, but really in general, you want to look at some kind of like approximate orbits indexed by finite subset of group. And what we're doing in this matrix setting is kind of analogous, but we're instead of looking at finitely many group elements acting on something, right, or looking at the finite approximation of an orbit, then what you look at is finitely many polynomials evaluated on the matrices, right? So you look at the traces of certain polynomials on the matrices or these non-commutative moments. So instead of group acting, you have non-commutative polynomials. And so then you have finitary approximation, which are matrices which have approximately the correct modes. And so then then this is what gives rise to the so-called one-bounded entropy, which is a kind of metric entropy for the setting, just like you would have for the dynamical and Sophic setting. And then in this case, though, when you're looking at dynamical systems, then there's a kind of contravariantness of this comparison, right? So in the dynamical system, you would look at sort of quotients of it, which are called factors of the dynamical system. But then in the von Neumann algebra setting, what you would look at is von Neumann subalgebras. So instead of the quotient, you look at subalgebra. And then also there's a kind of the free object in the dynamical setting is like the Bernoulli shift, and in this von Neumann algebraic setting, it would be a free product, or perhaps even von Neumann algebras of free groups. So if you look at this analogy, which is something that Ben Hayes has developed a lot, then you have this analog of the so-called Pinsker factor, right? So the Pinsker factor in dynamics is like you take the largest possible factor which has zero entropy. And then in this von Neumann algebraic setting, it would mean you choose the largest possible von Neumann subalgebra, which has zero metric entropy. So what is the conclusion of all this? What I want to say is that the maybe ultimate generalization of the technique that I've sketched in this talk is that these Pinsker algebras, or the maximal algebras with zero metric entropy, which are things that say containing the like objects that come from these Haar unitaries Uj, these Pinsker algebras are freely immutable. And this is maybe like a bit of a technical statement to absorb. Beginning the technical things like, okay, what is actually the von Neumann algebra where these things live? But what you have is that you create some kind of ultra product, right? Ultra product of matrix algebras. It's some kind of element. It's a space whose elements are sequences from of matrices from the larger matrix algebras. And the two sequences are the same if they're limiting, but if their distance goes to zero as n goes to infinity. And so in this ultra product, then you can identify elements that are given by the sequence of the random unitaries. And say Uj will be the element represented by the sequence. And then the result is that the Pinsker algebra, this maximal algebra with vanishing entropy, that contains this Uj, these will be freely independent of each other. So I think that now I'm out of time. Feel free to ask questions if you want to hear a bit more detail about this last statement, which I just sketched. And you can also look at what's written on the slides.
All right, let's thank the speaker and hit a reaction.